All right, I think we are live. Don't suppose anyone here has a device they could tune in on and check for questions. I think actually maybe I can do it. This is the most challenging part of doing the online lecture is knowing when there are questions. Well, it's YouTube, so, but it doesn't make any sound.
Right.
So,
Yeah. Yeah.
okay. I think this is going to work. All right, let's get started. We've got a fair bit of stuff to cover today. And moving on to hypothesis testing. So we did a bunch of descriptive statistics. We did some stuff just theoretical about sampling distributions and population distributions and experimental designs. And then confidence intervals last week was really the prelude to hypothesis testing, which is what we're going to focus on for the rest of the semester. So, and we're going to cover, let's see, we're going to cover some hypothesis tests for the population mean and population proportion, but really this is primarily about hypothesis testing in general and just getting you used to exactly what we're talking about. What does the p-value mean? What are the types of error that can occur in hypothesis testing? So first, a review of the confidence intervals. We use these to, when we are estimating a population mean from a sample and wanting to express what our uncertainty in that population mean is. So we can get a point estimate from the mean of the sample and then a margin of error around that point estimate, which expresses what range plus or minus from that point estimate we think that the true population means. And we talked about, you know, different levels of confidence, like 50% confidence, 90% confidence. And I think I convinced you that a 95% confidence interval has to be larger than a 50% confidence interval, because the more confident you want to be, the bigger and a range of error you have to give yourself. So that margin of error, it's the amount plus or minus your point estimate that you're going to put for your range of estimates on the population mean. When we're using the normal distribution and a 95% confidence interval, it's if it's not yet, will be famous 1.96. It's a good number to remember, but we don't always use it. We won't use it if we want something other than a 95% confidence interval. And only if we're using a normal approximation for the sampling distribution. So we'll do that if we have a very large sample, maybe greater than 300. That's where the t-distribution and the normal distribution look the same on your tables that you look them up. Or if we're constructing the CI for a proportion with n greater than 30. We always make the normal approximation for proportions where n is greater than 30 and NP was greater than, oh, I went to write this down and I forgot what the rule of thumb was that I had told you. I think it's greater than 5. I can never remember these rules of thumb. What's that? Yeah, it's for proportions. There's the NP rule. It's that you both want a reasonably large sample size, and you don't want either of your groups in the proportions to be too small. I think that it was 5, but I think I mentioned that in the last class. It said 10? Yeah. Okay, stick with 10. 10 is good. It depends on how how precise you want to be. There are exact methods using a binomial distribution to calculate exact confidence intervals, but it's nice when you can do it with the normal approximation. And of course, we also use the normal distribution if the population standard deviation sigma is known and the population standard deviation, or the population distribution, is normal. Whereas when we estimate the standard deviation from a small sample, we use the t-distribution instead. So I did the little fun survey, guess Professor Waldron's age. A lousy 6 of you answered the survey. So thank you to those of you who did for giving me something to analyze here. What I did, so in the survey, yeah, I should have taken names and then offered extra credit for the 6 of you who actually responded to the survey. I even went and tried to find a way to put it in the actual email so you wouldn't have to go to another website to fill it out. You just click the buttons in your email and that's it. So just so you know, next time I put hard work, sweat and tears into analyzing these data, so you can take 5 seconds to answer the fun survey. Anyways, I asked 5 things in this survey: to give a point estimate for your best guess for my age, then to give upper and lower bounds for a 50% confidence interval and for a 90% confidence interval. And I wanted to see how well you understood the concept of point estimates and confidence intervals. So they're each plotted here for these 6 guesses, and then I'll tell you what this is afterwards. But the point estimate is the dot here. In most cases, it's right in the middle of the confidence intervals. In one case, it's over towards one side, which is kind of interesting. It's an asymmetric confidence interval. So it's someone whose best guess of my age was 40 years old, but in this 90% confidence interval, they still thought I could not be more than 41, but could be as young as 30. Asymmetric confidence intervals are something that can come up with certain distributions. With a normal distribution and a t-distribution, we'll have symmetric confidence intervals. There's an equal margin error above and below. So in these cases, this amount above and below that is your margin of error. In this case, it's different. In the other cases, it's the same. All 6 who responded did understand that the 90% confidence interval should be larger than the 50% confidence interval. And you can see the differences in confidence, or I should use a different word here, the difference in self-perceived confidence in age guessing here. From the large or the small margin of error here to the very large margin of error here. This one up at the top I constructed by taking only the point estimates and treating them like a sample. So these are 6 observations, and I treated them as representative random, as a representative random sample from some population, and calculated the mean of them, that's this, and calculated a 50 and 95% confident, or 50 and 90% confidence interval using the, which distribution do you think I used? T. Yes, I used the T distribution. So, and you know how many degrees of freedom? Which T distribution I used? 5. Yep. T distribution with 5 degrees of freedom to calculate these two margins of error.
50% confidence interval without like electronically, like trying to find a local certain ones, you know, 90, 95.
Right. The table only gives you certain ones. I used the function for it in R, so I could just calculate it for whatever confidence interval I wanted. Yeah, you could take the closest one that's available if you looked it up in the table.
So how do we do?
Yeah, what are the results?
I'll tell you. Well, it's a much I got a much smaller sample this year than last year, so it's a bit hard to say. But the first, a couple things to note: the margins of error are smaller when I just took people's guesses and calculated it than people's own self-estimated margins of error. But in this case, there's actually there was a fair bit of bias in the guesses, meaning that they're not centered on my true age. Let's see if I can write on this slide here. That's tricky. Okay, my true age is right about there, 41. So,
That's exactly what I thought. I guess the whole your CV helped a lot.
getting extra information. So that's an example of getting extra information, like from getting a larger sample or something. You can decrease your confidence interval, but through additional information, so that you, at the same confidence level, you have a smaller margin of error. So I don't know. I guess 5 out of 6 of them, they're 50%. Or their 90% confidence interval included my true age, and 1, 2, 3, 4 out of 6, the 50% confidence interval included my true age. So in general, though, the confidence interval accounts for random sampling error, not bias like this. So if these had been centered on my true age, then these would have been overestimated margins of error. And I thought it was kind of interesting. I hope I remember to put this in. The ratio of the 90% to the 50% confidence interval, or the ratio of the margins of error. How much bigger is your 90% interval compared to your 50% interval? This is the theoretical answer. It should be about 2.8 times bigger to go to the 90% confidence interval. 2 of them were about there, but for most people, there actually wasn't enough difference between your 50 and 90% confidence intervals, I think. And this is just from a t-table looking up this would be the quantile of the 25th, or the 25th percentile, and the let's see, and the 45th here. So if you were looking at a normal distribution, the 50% confidence interval would be the 50% of the error above, or 50% of the area under the curve to the right and left of the center, 95% would contain 90% of the area. So what do you think, as your sample size gets smaller, what happens to that ratio? Like if we went, well, suppose first we went up to a normal distribution, so a large sample size. Would this ratio of the margins of error go up or down? Yeah.
Depends on distribution, if it's normal.
T-distribution, using the T-distribution.
Bigger sample is a little bit less chance for error, just because there's more to sample from, so we get a closer average to the actual.
Yeah, yeah. The fewer degrees of freedom you have, the fatter the tails of the T-distribution are. So the further out you have to get like to a 90% confidence interval, or to a 99% confidence interval, there would be a really extreme difference between the T with just a few degrees of freedom compared to the normal distribution. So for small samples, you end up getting very large, even larger and larger margins of error from the T-distribution. So let's move on to hypothesis testing. Any questions about the confidence intervals before we go on? So we do hypothesis testing when we want yes/no questions. Confidence or answers to a yes/no question. The confidence intervals are about estimating the mean and giving a range of uncertainty. And this is about an answer. For example, does a population have a specified mean, or do we have evidence that it is different from this specified theoretical value? Or does some intervention have a measurable effect in a treatment group compared to a control group? Here's some examples. Do hypertensive smoking men have the same mean cholesterol level as the general population? So there we would have a known fixed value for the general population gotten from some very large study like NHANES, and then some smaller sample that is our study population. Or does intermittent screening and treatment for malaria improve health and education of school children in a certain area? And this is a real example. Actually, I put a paper on that was trying to answer this question in the folder for today's session, and I'm going to talk a little bit about that as a motivating example today. So this paper is actually titled "Impact of Intermittent Screening and Treatment for Malaria Among School Children in Kenya, a Cluster Randomized Trial." So in this study, they picked out a sample of a number of schools in Kenya and randomly assigned them to doing nothing or to an intervention which involved regular screening and testing for malaria with treatment for any individuals identified as having malaria. Cluster randomized trials are beyond the context of this course. You will learn about hierarchical modeling by EPI2 and BIOS2 probably next fall for a lot of you. But the nice thing about what you're learning this semester about hypothesis testing is that even if you don't have the methods for analyzing something like this, you can still interpret the results of a paper like this, because you're going to see. So they have, they have a description. They have a bunch of descriptive statistics. And then they have results saying things like no impact of the malaria IST intervention was observed for prevalence of anemia at either 12 or 24 months. Adjusted risk ratio 1.03, 95% confidence interval 0.93 to 1.13, p equals 0.621. And at 24 months, adjusted risk ratio of 1.00, and there is a confidence interval and a p-value. So this is a very common and good practice to report both your point estimate, your 95% confidence interval, and a p-value. So these sort of go hand in hand, and they provide complementary information. Ordinarily, it would have to be under, the p-value would be under 0.05 to consider it significant.
And because null hypothesis is in between the interval.
Yeah, so I'm going to talk about that a bit today, but these are alternative ways to do if it's a one sample hypothesis test. So here, this is a one sample hypothesis test because they are, well, sorry, this is a two sample hypothesis test. They have a treatment and they have a control group, and they're reporting the ratio of risks for anemia. And then they're giving a point estimate for that ratio. We will cover risk ratios and odd ratios later this semester. And they're also reporting the confidence intervals. So you can tell by the fact that this confidence interval includes 1, and also by the fact that the p-value is greater than 0.05, that they are not rejecting their null hypothesis. And they're concluding there is no evidence that this treatment is effective in preventing anemia. And then they talk about why that might be.
Well, they save a bunch of money on spending, like they thought this was effective and they want to spend all this money on it. It wasn't.
Yeah, I'm sure it's not what they're expecting. They have some, I don't know, what did they say? Oh shoot, it's so sensitive. Marked geographic heterogeneity in transmission, rapid rate of reinfection following treatment. So this first one, I don't know. The second one, they're saying that maybe the treatment basically is not effective because it is not continuing, and the individuals at risk for malaria continue being at risk. So basically, the treatment isn't doing anything for them because they're reinfected right after treatment. Mm-hmm.
The same place keeps getting the same effect.
Right. Yeah. And the rapid rate of the variable reliability of RDTs. I forget what RDT stands for. Rapid diagnostic tests. So they're all, again here, blaming the effect. So it's both the effectiveness of the diagnostic test, the effectiveness of the treatment, and the relative contribution of malaria to the etiology of anemia. And there are other causes of anemia besides malaria. This is why we do randomized controlled trials, because it's you can get answers that are not what you're expecting. They're very formally done so that you cannot massage the data to make it look different than what you found generally. So in setting up a hypothesis test, we always have a so-called null hypothesis and an alternative hypothesis. The null hypothesis, would be a usual distribution that we have seen in the past, or in the case of that previous one, the control distribution, so the usual rates of anemia being what happens in the absence of any intervention, and then a potentially new distribution induced by an intervention or some condition that is changed from what we are accustomed to. And this would be the alternative hypothesis if this potentially new distribution really is new. I'm going to talk primarily about one sample inference today, where we have one sample and we want to know if it came from a known previous distribution. And a classic example of this would be you have a handful of beans, a few of them are, or very few of them are white, and then we have a big bag of beans here and most of them are white. Is this handful from this bag? And depending on your sample size and just how many of them are white, you might say probably, yeah, they could have been taken from this bag, or probably they were taken from another bag. And obviously, if you have 100 beans in your hand and none of them are white, then they probably didn't come from this bag of mostly white beans, whereas if you only took 2 of them, you're more likely to get just 2 beans of the wrong color just by chance. And that's basically the way the one sample hypothesis test works. That big bag of beans is what you know, it's what you hypothesize as that's your null hypothesis. And then you take a sample and infer whether it was likely to have come from that null distribution or not. Yes, question?
Okay, so let's apply this to our epidemiology studies. Since you mentioned earlier, if it's 2 sample hypothesis, it's more likely comparing the risk ratios. So if it's only 1 sample hypothesis, is it more likely for the study of like cross-sectional study? So there's no, I don't know if I'm putting it wrong, like there's no temporal order, so there's no comparison. It's more like a prevalence study, so there's no risk ratio.
Yeah, it would be about prevalence.
Okay.
So in the most typical sample. So perhaps something about prevalence where you have a known nationwide prevalence from some large national study, and you just want to look at the prevalence of one specific group to see if it differs from this very accurately known prevalence.
And then if you test the risk ratio, that will be more likely for the 2 sample hypothesis.
Right. Yeah. Risk ratios are by definition from 2 samples. Just check if we have yeah, I think we're live. Can't tell. Okay. Okay. This is a classic analogy to the courtroom trial, where we have a defendant who's been accused of a crime. The null hypothesis is of innocence, and the burden of evidence is on guilt. So what you would accept the innocence in If there is no evidence, you accept innocence, so that would be the equivalent of the null hypothesis. You accept the null hypothesis until you have evidence to reject it. So then the prosecutor tries to prove the guilt, the alternative hypothesis, and only if there is sufficient evidence to reject H0 as improbable, then we accept the null hypothesis or guilt. So we have a couple ways that we might make the right or the wrong decision here. If the null hypothesis is true, the defendant is not guilty, and we accept the null hypothesis, that's a right decision. And of course, also, if the alternative hypothesis is true and we reject it, that's also the right decision. But if H0 is true and we reject it anyways, that is a type 1 error. That's what we control with the p-value. Right, that's a type 1 error. And the probability of that happening is what we control by requiring a p-value less than some cutoff. So by requiring a p-value of less than 0.05, we're trying to control the type 1 error rate, the probability of convicting an innocent person. On the other hand, if H1 is true, so the defendant's guilty and you fail to convict, that's a type 2 error. So that's where you fail to reject a true alternative hypothesis. And as you can imagine, there's some trade-off between these two. The more confidence you want in not making a type 2 error, so the lower your type 1 error rate, the higher your type 2 error rate will be, and vice versa. So if you decide that you never want to release a guilty person, the only way to do that is to convict everyone and to have a very high type 1 error rate. Yeah, it's something to keep in mind when you hear, discussions. Whenever I hear about, something about what went wrong when a convict was released from prison on parole and committed a crime again, I think about type 1 and type 2 error rates.
In the type 2 error, like the type 1 error. I feel like I'm more okay with allowing that to happen.
Yeah, well, it depends on the context. In the context of criminal justice, there's the old saying that it's better to free 10 guilty people than to convict 1 innocent person. I think so too. I guess not everyone agrees with that, but this trade-off between type 1 and type 2 errors is a judgment decision. There isn't a right answer to that.
This goes back to specificity.
Does this go back to specificity and sensitivity? It's related. Yeah. It is. I'd have to think about the exact relation between them, but it is related. It has to do with in that case, it was thinking about true positives and false positives, but it was thinking about individuals and not about hypothesis tests. But it is the same kind of trade-off, and where to get improvement on one, you have to give something up on the other. So, as I mentioned, the confidence intervals can be used as an equivalence to hypothesis testing, at least in the case where it's a one-sample test or where the confidence interval is on a ratio, as we saw with the risk ratio, so that there's a single point that we're comparing it to, like a risk ratio of 1. So the equivalence is that, so here's a normal distribution, and we would build a 95% confidence interval going between -1.96 and 1.96 on the standard normal distribution. Or alternatively, if we calculated a z-score as our test statistic, we would reject the null hypothesis if it came out to be something greater than 1.96 or less than minus 1.96. So there are equivalent ways to test your null hypothesis. Oops. Here are 5 steps to hypothesis testing, and I want you to actually go through them, both, especially now as you're getting started out, but as you continue on too. I think it's very easy to do your test, get a p-value, and make a decision without actually going through all these steps. And it's actually easy to make mistakes, especially in cases where the alternative hypothesis is a little bit non-obvious, especially in the case of one-sided alternative hypotheses, which we'll talk about. First step is to explicitly state your null and alternative hypotheses. So you actually write them down. What is H0? What is your H alternative? That makes it very clear what you're doing. At this point, you specify your significance level before you've done the test. At what level alpha are you going to reject the alternative hypothesis? It's usually 0.05, but not always, and it's worth stating what you're going to consider to be a significant finding, what your allowable type 1 error rate is. At this point, you go ahead and draw your sample size n, and compute a test statistic. It might be a z-score if it's something where your sampling distribution is normal, such as for a proportion with n greater than 30, or for when sigma is known. Whereas if it's a continuous variable and a small sample and you're estimating standard deviation from the sample, it'll be a t-distributed statistic. You'll still calculate a t-score, but it will be assumed from a t-distribution. But this is a very general procedure. Any hypothesis test you do, your step right here is going to be to calculate a test statistic. That might be a chi-square test statistic, might be any number of different things, but you'll calculate a test statistic, and it's something where under the null distribution, you know theoretically what its distribution is. And because you know what its theoretical distribution is under the null hypothesis, you can then go and calculate a p-value. And your p-value, anyone want to explain to me what the p-value is in terms of your null distribution? Yeah.
So it's the probability of finding your test statistic, given that the null hypothesis is true. You finding your test statistic or greater, or
exactly. It's the probability of finding your test statistic or something more extreme if the null hypothesis is true. That's exactly right. You then compare your p-value to your significance level alpha and decide whether or not to reject H0. If it's less than alpha, you reject H0, otherwise you do not reject it.
So it's the probability of finding your point estimate in your confidence intervals?
It's your probability of finding your test statistic. So I could restate this in terms of how to do it with a confidence interval, but I'm just stating it as the test statistic for now. This is this is a very general framework, valid in settings where you can't calculate a confidence interval. But yes, you could. If you did it in terms of a confidence interval, you would not calculate a test statistic. You would calculate a confidence interval. You would not calculate a p-value. You would just determine whether your theoretical point value for the population was contained in your confidence interval or not, and then you would decide whether or not to reject H0. And then finally, state the conclusions in terms of your subject matter. What does this mean in terms of what we set out to study? So to go into these in a little more detail, formulating the null and alternative hypotheses. Again, the null hypotheses is always one of no difference. It's what you would assume in the absence of any evidence. So it assumes that the treatment has no effect compared to a placebo, or that your prevalence of your sample is the same as it's known to be in the population. And if it's true, then any discrepancy you see in either in your sample mean from that null value or in your test statistic is just due to sampling variation. Nothing else. So there's no systematic difference. It's just sampling variation. Your alternative hypothesis is that there is a real difference, that the sample you've drawn is not compatible with the null hypothesis. You've got too few white beans in that handful that you took for it to have come out of this sack of beans. And if so, given your sample, the null hypothesis seems very unlikely, we'll reject the null hypothesis. Most of the time, you're going to use two-sided alternatives, which looks like this. Your null hypothesis for one sample would be that the mean of your study population is equal to the mean of your theoretical population under the null hypothesis. And the alternative is that it is not equal. So there's no specification of greater or less than, just equal, not equal to. For example, is the blood pressure of smoking males the same as the general population? Null hypothesis is that it is, alternative is that it's different. We're not hypothesizing about whether it's greater or less than. With two samples, there's no theoretical value from the population. It's just that the mean of the populations from which these two samples were drawn are equal. And I changed there. And the alternative is that they're not equal. Or alternatively, that the difference between them is 0. Same thing. So an example of this being the RCT example that we used. Does intermittent screening and treatment for malaria affect the prevalence of malaria in school children? The null hypothesis being that the prevalence of the control group is equal to the prevalence in the treatment group, and the alternative being that they're different. And this is what that paper used. Occasionally, we will also use one-sided alternatives, which means that there's an inequality in both the null and the alternative hypothesis. So for example, in the one-sided test, that the mean of our study population is less than or equal to the mean under the null hypothesis. Notice that the equality is included in the null, and there's no equality included in the alternative hypothesis. So it's not H0 less than HA greater than or equal to that. It's HA just greater than. Or for two samples, it's that one of your sample means is less than or equal to the other. And the alternative is that it is greater. Of course, the inequality could be in either direction here. Question?
So in the example of the malaria and anemia thing, weren't they actually interested in whether the treatment protocols improved
Mhm.
so that therefore there would be less cases of anemia? So wouldn't a one-sided test have been more?
Good question. So in that RCT example, they certainly performed the study hoping that treatment would improve the rates of anemia. So why don't they do a one-sided hypothesis there, since their alternative, since their preferred hypothesis clearly is that the rate of anemia in the treatment group will be less than in the control group. It is generally not kosher to do that because yeah, how can I I'm going to show you in a bit how
Of course, there would be a possibility that it could actually make it worse,
Mhm.
right? But are they like interested in that, or?
It's not so much about whether they're interested in the alternative in that alternative. It's that for one thing, your p-value, as long as there is a reduction, will be half of what it is in the two-sided test. So it makes it easier to reject your null hypothesis. So it's generally frowned on by journals to do that. And unless the other side is really not a possibility, it's not appropriate to do. The situation in which one-sided tests really are appropriate is the test of no harm. So if you were going to an alternative, your treatment is something that you're doing because it is cheaper, and your hypothesis is that it is no less effective than the control group, the standard of care. You may actually want an alternative hypothesis that is one-sided, with your treatment being less effective than your control. Because you have no grounds to believe that it's actually better than the control. In that case, it's also a conservative thing to do because it makes you more likely to reject your null hypothesis of no harm, which is also what makes it a more appropriate thing to do, if that makes sense. But in a case like the effect of treating malaria on anemia, I think it would be inappropriate to use a one-sided test there because there is a possibility that I don't know, through some unintended consequence, who knows, perhaps it is actually harmful. It's not impossible, so you can't treat it as if it's impossible. Very good question. Oh, here's my discussion on it. Yeah, it's controversial because the one-sided test gives you small p-values. A lot of journals will ask you to say in your abstract that all tests of significance are two-sided for this reason, or to clearly justify it in advance of the test, which would be difficult to do in most situations. i.e., there's no reasonable possibility of another alternative hypothesis. The step 2, setting alpha. It's typically 0.05 or 0.01, some small value. And this controls the false convictions. This controls the false thinking that an ineffective treatment really is effective. Yeah.
I don't know if I'm clear on the difference between alpha and your p-value. Are they?
So clear on the difference between alpha and the p-value.
Yeah, are they the same?
No. Alpha is a decision you make in advance of doing the test. It's saying that I will consider this as a critical value for deciding whether or not to reject my null hypothesis. Whereas the p-value is a probability that you calculate and then you compare that to alpha to decide whether or not you reject your null. So step 3, calculation of the test statistic. You'll get lots of practice doing that in the case of comparing one mean to a theoretical value. Your test statistic will be the z-score, which is your mean of the sample minus your theoretical mean divided by the standard error. So standard deviation sigma over square root of n. And if you're using S here, it's the same calculation except that your theoretical null distribution will be a t distribution. The important thing is that you have some formula for calculating a test statistic at this step. This is how you can think of it in terms of your distribution. H0 is some theoretical distribution. Here, a normal distribution if you're doing a z-test. Your H0 value, your theoretical mean, is right in the center. Then your p-value, well, if it were a one-sided, you get a sample value of your test statistic. If it's here, your p-value would be this under a one-tailed or a one-sided alternative, and it would be twice that, the left side also under a two-sided alternative. Question?
And so if you have just a one-sided, can you no longer state the confidence interval as between plus and minus?
Good question. If you have a one-sided alternative, can you still state a confidence interval? There is such a thing as a one-sided confidence interval, which we don't cover in this course, but it is possible, and it only has a margin of error in one direction. And it would involve calculating one tail of this instead of two. And that margin of error would be different. So it is possible. It's very rare that you would want to do that. I suppose one situation where you might do it is if you have a theoretical limit of plausible values on one side, like you can't have values less than 0, and your point estimate were 0.5, you can't have a population, and you can't have a population mean less than 0. You might add something to the positive side to account for that extra certainty that you've gained on the negative side. That's one example of a sort of a partially one-sided confidence interval. I'm not going to ask you to calculate any of those in this class, just because the chances of you even coming across them are pretty slight. In step 4, you take that value of the test statistic, use your theoretical null distribution, either in the form of a table or your software, and convert it to a p-value. So for the z distribution, all you need is your z-score. For the t distribution, you also need the degrees of freedom. We'll get into a chi-square distribution. You also need degrees of freedom. But in all of these cases, you'll decide, am I going to look at 1 tail or 2? And what is the probability under the area of this theoretical null distribution beyond the test statistic that I observed? That's your p-value. And you can think about it, as we said before, what's the probability that we would observe a value of what we saw or more extreme, or what is the probability in the tail or tails of this sampling distribution under the null hypothesis beyond where what we observed. And then based on that, if your p-value is less than alpha, you reject the null hypothesis, otherwise you don't. Simple. And then make conclusions about your question in terms of the subject matter. Yes, question?
And I'm sorry if you have already discussed this, but how do you determine what alpha is ahead of time? I know that it's just, you know, the value you're saying.
Yeah.
That you're finding your statistical value is relevant or not, but how do you?
So how do you determine alpha? It's really a subjective decision. It depends on what the relative cost of a type 1 error versus a type 2 error is. If the cost of a type 1 error is very high, then you set alpha small, like in the criminal justice example. If you think that the cost of a wrongful conviction is very high, then you would set your alpha very small. You would want to make the probability of that wrongful conviction very low. There are other situations where the cost of a type 1 error is not so high, and maybe you don't want to make a type 2 error, and you would set a more, you know, relaxed threshold on alpha. I don't know, maybe for air quality testing or something, where you want to know if a sample you're testing for air quality has a different mean number of particulates than compared to the normal value. Maybe you want a more relaxed threshold for deciding that there's been a change. If you don't know, then you probably choose 0.05 because that's what most people choose. But there's nothing magical about 0.05, and yeah, I think you shouldn't treat a p-value of 0.07 as being meaningless. It's still probably more likely than not that your null hypothesis is false. If you have a p-value of 0.07, I would still want to bet even money on it. But at that very high threshold, then you're not rejecting it. Yeah.
On our tables for like t distribution, z-score, that 0.05, is that related to like the 95%? I mean, that's what it kind of looks like when you look at the table. It says 2-tail 0.05. That's your 95% confidence.
Yeah. So the alpha of 0.05 is related to the 95% confidence interval, and that at that threshold you have 95% of your error within those bounds and 5% beyond those bounds.
So they're both like, they're just chosen in that same way, right? Whatever you're comfortable with.
Yeah. Yeah, 95% confidence sounds good. I don't know. Maybe I should have asked about that in the fund survey instead of 90%. Maybe more people would have answered that. You know.
Yeah, just like confident.
90% was just too weird, and 50%.
That's short.
Yeah. All right. There's the summary again. I'm not going to belabor it anymore. Oh, and we're very short on time. Here's something for you to think about here. these are the kinds of questions that you should ask yourself when you read a paper with statistical findings. They'll, I think, be second nature at a certain point. What's the outcome variable? Here it's a risk ratio between treatment and control groups. What are the null and alternative hypotheses? The significance level alpha, the p-value, was H0 rejected or not? Those are just the basics of setting up and making conclusions from a hypothesis test. There are a couple examples here that you can actually calculate through. I encourage you to do that. You know, these will be, these are just nice, typical, straightforward questions. There are a couple, by the way, if you go to our YouTube page and to playlists, I have examples for doing all of this sorts of things in SPSS and doing it by hand, just short videos on how to do those. Yeah, we don't have time for this. But you can see it's very formulaic here. It involves, you know, figuring out what your sample mean is, what your mu naught, your mean under the null distribution is, calculating your test statistic, getting from that a p-value that you can look up in a table or use software to calculate, and then deciding whether or not to reject or null. You'll get lots of practice in this in the lab.
So under
Yeah.
0.05, you reject it.
If alpha, if your p-value is less than alpha, you reject the null. And often alpha is 0.05. And yeah, again, we usually use two-sided tests, except under very special circumstances. Oops, that was a repeat. You'll use these same steps for testing hypotheses on proportions, such as in surveys, polls, or prevalences. And, oh, geez. Look at that. You can think of no event, such as in that RCT, that would be no anemia, an event being anemia being a 1, and then you can just think of this as a z-test on means, where your variable x takes on values of 0, 0, and 1. If your mean, then the mean of the zeros and ones is p hat. That's your proportion. So the number of ones divided by your total sample size, and your theoretical mean p naught is just the difference divided by the standard error again. And then you use the z table in just the same way. So it's really not much different. It's just a little bit different stepwise as you go through the actual calculations. Question?
That standard error, those p-hats percentages?
They would be proportions. So they would be like between 0 and 1.
So if you have 1,000 and your p is 50%, is that 0.5 or is that 500? If your proportion were 0.5, this would be 0.5 times 0.5, so 0.25 divided by 1,000 and the square root of that. Yeah. I was doing a problem before class like that,
Mhm.
and I got a crazy small standard error because the n was so large.
Right.
So I converted the p's to 500, not 0.5, and it made more sense. But I was probably just fishing for the answer.
Well, so actually, if you multiplied these by, if you use percentages, you would have an extra 2 hundreds in here, and the square root of that is 100. So you would just end up with a standard error given in percentages. So you can do it either way. I prefer doing it with proportions, but yeah, it'll work. You'll end up with a standard error 100 times larger. We've talked about this already, but the hypothesis test and the confidence interval are strictly related in that if the confidence interval contains mu naught, your theoretical value under the null hypothesis, then you won't reject H0, and if it does, you will reject H0. And if your confidence interval is, or sorry, if your type 1 error rate is alpha, your confidence interval will be 100 times 1 minus alpha. So 5% alpha is a 95% confidence interval. Simple as that. There's one common misconception about this, though, which is when you do 2 sample tests, if you calculate a confidence interval for each one of those samples, the fact that they overlap does not mean that you are not going to reject your null hypothesis. So for them to be equivalent, you need a single confidence interval compared to a point value for the population. In the example of that RCT, they gave a single confidence interval for the risk ratio, and that would be compared to 1. You notice they're not giving a different prevalent. They're not giving the prevalence for the treatment and the control group and then seeing whether those overlap. They're actually calculating a single confidence interval for the risk ratio, the ratio of risks for the 2 groups. Does that make sense? So if you draw two intervals, so in that example of the guessing the age, just because there's some overlap between those intervals doesn't mean that those 2 people think that I have the same age. There's like a little bit of overlap in their agreement, but even if those are 90% confidence intervals, you might be more than 90% confidence interval, more than 90% confident that their point estimates are different. Does that make sense? Remember that. I've been told that in future classes, this comes up and lots of people are confused. So, and that think that overlapping confidence intervals mean that you don't reject the null hypothesis, and it's just not true.
So the rejection is purely based on that value of 1.
Yeah, the confidence interval and the hypothesis test are only equivalent when you're comparing one confidence interval to a theoretical point value of the null hypothesis. And if it includes that point value, then you don't reject the null. And even when you have 2 samples like the RCT, like when we have 2 means, what you will do is calculate a confidence interval for the difference in the means. And if that confidence interval includes 0, you do not reject. Okay. Just a brief note on power. I mentioned type 2 error a little bit before, and I'm going to talk more about power next week. But remember the type 2 error was when H0 is false, but we fail to reject H0. So that's like the guilty person who is not convicted. That's the type 2 error. And then 1 minus that is the power. So, and it's also called the power to detect a difference. It's the probability that if H0 is false, you'll reject H0. So you'll talk about the power of a study. If you're designing a study, you're designing an RCT, you're going to want to calculate the power in advance. So you'll posit some true difference, and you'll want to calculate the probability that given your experimental design and given your sample size, you'll be able to detect a difference of that size. That's power estimation. And we'll just touch on it briefly next class. So just a few things to keep in mind about all of this. As your type 2 error decreases and correspondingly power increases, that happens either as your alternative hypothesis value is further from the null hypothesis, or as the standard deviation decreases. So that's like your precision of the measurements improves. So the amount of overlap in your null and your alternative hypothesis distributions, the amount of overlap decreases. Your type 1 error rate, alpha, stays the same. That's regardless of what your mean under the alternative hypothesis is. And in general, we want a power that is as high as possible for a given practicalities, given the costs of doing a study, collecting samples, etc. That's what protects you from reporting. So yeah, alpha is what protects you from spurious results. Power is what protects you against not observing true results.
So I guess the cost benefit of that would be different depending on the example.
Yep, that's right. Yeah, in the power
would be like different than
in the power calculation, the things that you'll generally consider are, how big of a difference is actually meaningful, important, how big a sample size do we have or can we have, and what type 1 error rate and what power do we want. There are 4 things: type 1 error, type 2 error power, sample size, and the true difference between your study population and your null hypothesis population. And given any 3 of those, you can calculate the 4th one. And that's what you do in power calculations. You're going to use t-tests just the same way that I've been showing you with the z-test here, except you'll use the t-table instead of the z-table. One more common misperception here that I'll end on. If we fail to reject H0 at our type 1 error rate of alpha, then is the probability that H0 is true equal to 1 minus alpha? So if we have alpha of 0.05, we fail to reject the null. Does that mean that our null hypothesis is 95% probable of being true? How did you know? Does that sound right, or does that sound strange? What's that? It doesn't. Do you believe me? You do. You don't believe me? Yeah. Well, so we have a type 1 error rate set at 0.05, meaning that there's only a 5% probability that if the null hypothesis is true, we're going to reject it. That's what type 1 error is.
Right, you said alpha, and it's
Mm-hmm.
0.5.
So
and it has the 5% without, like
So-
outside of the
So that tells us if we reject the null hypothesis, what's the probability of our being wrong. But it doesn't tell us anything about if we don't reject the null hypothesis, what's the probability of being wrong. So the example of the I don't know, which example do we want to take here? The bag of beans, you pull out your bag of your handful, and it has, you know, it has a number of beans that's not too different from what you would have expected if it came out of the bag. Does that mean, so if my null hypothesis was that the mean number of white beans or percentage is 50%, and I pull out 3 beans, 2 are white, 1 is black, I can't reject the null hypothesis that they're half and half. Does that mean that we can be 95% confident based on these 3 beans that they came from a bag that's 50% of each? No. It doesn't tell you anything about the true probability of that null, about the probability of that null hypothesis being true. That's right, you're only controlling type 1 error. Based on that, you have no information about the type 2 error.
I just wanted to clarify, but if you do reject the null, then the probability that the null is true does equal 1 minus alpha?
Nope. If you do reject the null, the probability, or the probability that the alternative hypothesis is false is 1 minus alpha, or that the null the probability that the null hypothesis is false is 1 minus alpha. But you could imagine there are many other possible explanations other than the null hypothesis being true. So it doesn't mean that the probability of the null hypothesis being true is 1 minus alpha. It could be that, you know, the true mean, you know, if our null hypothesis was a prevalence of 0.5, you know, we might have failed to reject it, and the true mean is, or proportion is 0.4 or something else. Did I answer your question? Because you asked if you do reject. If you do reject it, then you could say that the probability of the null hypothesis being true is less than alpha.
Okay.
So less than 0.05. And finally, statistical significance does not necessarily mean practical significance. So especially with very large samples, you can get a small p-value with a very small difference that in practice doesn't really mean anything. Yeah.
So what is statistical significance? Practical significance.
Practically significant is not something that you determine by statistics. That's just based on your knowledge of the area and how big of a difference actually matters.
I feel like it's always nice to have like the statistical backup.
Yeah.
You know something makes complete sense when you say it, so people are just not going to get it unless you give them statistical.
So without statistical significance, you have no evidence of a difference at all. There might be no difference. So then it's not practically significant either. But statistical significance does not necessarily mean practical significance. You might say that it's a prerequisite. All right, and I need to let you guys get down to the lab. Taking up all of the time here.